let's start our seminar. No, what homework did you do? What exercises did you do?
As I said, Tor 1, 0, 1, x 0, 1, zn, zm.
Okay, yes. First, Tor over z, n, zm. Tor, yes, no, all Tors and all X's. And no, maybe Tor 1 over any ring, yes, between no, some generalization, yes?
Yes. I thought we need there that are commutative, no?
In general, no. It's not commutative ring. This is right ideal, this is left
yes.
ideal.
You're right.
It's not important, in fact. Okay. You're welcome.
So first,
У него. Все, хорошо. У вас это все,
Да-да.
пардон.
so first I'll calculate Tor for zn, zm. So obviously there exists such projective resolution. So this is projection on M, this is 0. Yes. So
And you apply, for example, tensor product with z modulo m.
yes, I multiply it by z modulo n and obtain. So okay.
If you tensor something with ring itself, you obtain the same module. Yeah, z m, and multiplication by n, and nothing else. No, you did not this p tensor ID to calculate Tor. You need to eliminate the right term. Yes.
Yes, of course.
Okay.
So I just
No, and
eliminate
yes,
it and
yes.
write 0 here, as you said.
Because this sequence is not exact.
Yes.
It has.
Now I want to say that I want to use. Okay, I'll write here. So I want to say that we have an isomorphic sequence. This isomorphic sequence.
Of course, and multiplication by n.
Goes multiplication.
No, so you only need to calculate kernel and co-kernel of multiplication by n
Yes.
in z modulo m.
Yes. So yes, from this isomorphism, I get that Tor
Tor 1 is kernel, yes.
1z, yes, is a kernel. Isomorphic. Okay, right, just Tor 1. Kernel of this multiplication map. Which is nothing but this k from z10 such that nk is 0. Yes. So
And what is it? It's some subgroup in cyclic subgroup, so it's cyclic.
yes, yes, it's subgroup of cyclic group.
And
Every cyclic subgroup is cyclic, and I claim. So if we take
what is generated?
if we set D is greatest common divisor of n and m, so I claim that this is indeed generated by this not D, but here I denoted. So okay, I'll move it. I have another notation.
Something like m divided by d, yes?
Yes. So we need to take n. So since it's common divisor, we can write it like this. So just because it's a divisor.
It's n or n?
N. N and m is d of m prime. Yes, and now I claim that this is generated by m prime, which is nothing but m divided by d. So the proof is simple.
No, it's more or less obvious that this element has order D,
Yes.
so it's a cyclic group of order D, and why it's generator of the kernel?
So first of all, it lies there because we have we can write like this. So
No, yes, it's in kernel.
It's,
yes,
it's,
more or
it's
less
obvious. Yes. And it's 0. Then it's in kernel.
And if any, yes, if any k, if you have k and k divided by m, yes.
Let's see. I forgot what my argument. Let's see.
Oh, yes, so you consider k and in kernel. This means that n multiplied by k divided by m is divided by m.
Is 0 in this group.
Modulo m.
Yes, modulo n in this group. This means that.
And k divided, no, it's m something, yes.
Yes. P. And what I write, I say that okay, so I guess my argument is not complete. I don't see why I thought that this is, from this follows.
No. No. No, let's write down n as n prime d in the left hand side.
Yes, you're right.
And then let's eliminate d. You obtain n prime, k is m prime p, yes?
Yes.
Okay? And then you need to say that m prime and n prime are coprime integers. So if left hand side is divided by m prime, then left hand side is divided by m prime. And then in fact k is divided by m prime. Because n prime and m prime are coprime, okay? I don't see what you write, right? But I think it's true. No, yes, n prime and m prime are coprime. Right hand side is divided by m prime, so left hand side is divided by m prime, and then k is divided by m prime. No, I think that k. No, you need that k is divided by m prime. Yes, it's your claim.
Yes, yes.
No, right hand side is divided by m prime. Yes?
Of
so
course.
Yes,
of course.
So k is divided by m prime.
Yes, you are right. You are right. You are right.
It's divisible by m prime.
Prime. Okay.
It's because n prime and m prime has common divisor or greatest divisor is 1. Yes.
Yes, because of this.
Yes. No, and so it's our claim.
Yes. Yes. Okay. Then this means that then this is done. This is
no. In fact, all these implications are equivalences. So in fact, this it's proved that these elements in kernel. It's more or less it's all equivalences. Okay.
Yes.
No, yes.
And of course, yes. And just by definition, this order is D. Hence.
So it's cyclic group of order D. Yes. Okay.
Yes, this means this is amorphic too.
Now what about Q-kernel? It's more or less in the same manner. Yes. Number theoretical. Undergraduated number theoretical. No, more or less of the first course, I wouldn't know, or something like this, yes. No, divisibility of integer numbers, yes.
Yes, and for Tor 0, we also have such a
co-kernel.
So do I need to say it, or is it?
No, yes, okay. Yes.
So for Tor, so just by that, from this isomorphism, I also get that Tor, this was Tor 1, yes. Tor 0 is, so Tor 0 is isomorphic to the kernel. Kernel was everything, and the image was, yeah. So
we know that, in fact, it's isomorphic to tensor product of Zn and Zm, yes?
Yes,
at the same time.
Isomorphic.
But now we see this in this form. Yes, okay.
Yeah.
And why it's isomorphic to the same thing?
So, and I claim that this is isomorphic to ZD. Yes. The proof is.
Which generator? Wait, what's the generator?
So I have so the generator. If you want the generator, I believe.
No. If you don't want the generator, let's prove what as you wish.
I believe the generator is something like okay, something
okay,
like.
Okay, let's see. If you give us the implicit, the explicit isomorphism, then I think we will obtain.
Isomorphism is like this. So if we have the map like this, so it goes like this, k to k. So obviously this is a surjection. This is because this is a less number than n.
It's not less, it's less in sense of divisibility, yes.
Yes.
Divided by m. So this is correctly defined, yes.
So we need to check
that the kernel is exactly n zm.
Yes. So if we take x from n zm, yes, we need to check, as you said, that this is indeed the kernel. We can look at phi of x. This is so since it's from here, this is n times k, some k, and this is we can.
No, this is obvious direction. Yes.
Zero. Yes.
Because n is divisible by d. Okay, in the opposite direction, if you have x from kernel, so x is divided by d.
Yes. And we need another direction. So if we have a kernel, an element from kernel, phi. I think I'll write here because it's hard for me. So if we have an element from kernel, this means that by definition phi of it is 0. This means that x is d on some y. Because this is in.
It's 0 in z
yes,
modulo d. Yes.
This is modulo d, and this is in integer numbers. Yes. This means that there exists some u such that if I multiply u by n prime, this is 1, and this is modulo n prime. So this is because
n prime and n prime are coprime.
Yes,
again.
this is because GCD n prime is 1. Yes.
No.
What do you mean?
It's true, but I think that's not implication. Just true. It's just fact. It's not.
Yes. It's not implication.
Not follows from this.
It's
yes.
comma. Okay.
Yes.
So now let key be u plus y. Yes. And now consider the. So it's just basic arithmetics. I don't know, but nevertheless. This is by definition n prime times u times y, and it equals to y modulo m prime because we have this equality. So now real implication. Now if we consider n times t. This is by definition d times n prime times t, and I just expand. So yes, I just expand everything here, and u times y. And now this is just d times y, and this is just text. This is just text and modulo m. Yes.
Yes. So what we.
Yes,
claimed, yes, okay.
We see that x is in n.
Okay. Okay. Yes.
Yes, and we obtain that the image is
Yes. Okay.
isomorphic to this time.
N. Okay.
Yes.
Good. So, what about X? No X.
Yes.
No, X are the same, but in X1 isomorphic to Tor0, yes?
Yes, yes.
No, but they all isomorphic to the same abelian group, yes.
It turns out that our X's are really the same. So how we can see it? So assume.
No, the same projective resolution, yes?
Yes, the same projective
Of the
resolution.
N. No, if, when you consider Tor, you also could consider projective resolution of the M, yes? But here you need either consider projective resolution of the N or injective resolution of the M. It's another solution.
Yes, but I consider
No,
the free projective resolution. So when I use Hom on this, and throw away the last, not the last, but I mean, throw away this guy. Z, yes. And throw away the first one. So this is multiplication by n.
Yes, and here, this is the zero term, yes, and this is the first term, yes, in the opposite direction.
Yes.
So this is zero homology and the first homology.
Yes, because it's co-homology.
Yes.
And once again, I can take an.
No, you obtain the same chain complex, but now with arrows in the opposite direction. Yes. It's co-chain complex.
Not really opposite; they are in the same direction. But
no, now they increase degree. So in some sense they are in opposite direction. Yes, they increase degree.
Yes,
it's zero, and it's so x1 it's co-kernel, and x0 is kernel. In Tor it was the opposite things. Yes.
The maps here go like I take, so I take k and send it to phi k, which is phi k by definition.
No, yes, it's sense 1 to k. Yes.
By definition.
Yes, of course.
So and this is commutative.
Of course.
And hence, so I not calculate it. I have
it's the same thing.
The same thing.
The x1 here, it's co-homology, it's co-kernel of multiplication by n. It's as Tor 0.
Tor 0, yes.
No, it's the same. It's modulo.
X1 is Tor x1
Okay,
to 0.
okay.
Yes.
What do you think? What's the injective resolution of z modulo m? No, for example, if you wanted to calculate x by injective resolution, for example.
Q modulo z, maybe.
Yes. If you consider q modulo z, and then multiplication by m, it's surjective because it's divisible, and its kernel is z modulo m. It's injective resolution, and you could calculate x by this injective, and you obtain the same result. For example, for z, it's this injective resolution. You can embed it q and then q modulo z. It's injective resolution for z, and also you could calculate, for example, x from z modulo n to z by this resolution, something like this, and obtain the same result. Okay, if you're interested, you can do this. Okay, nice. What about this thing?
Yes. So once again, I consider just the
No, yeah, this.
I consider shorting the sequence. So this is resolution now.
No, yes, it's not resolution, but it's a short like the sequence of modules, so you obtain longer sequence in Tor, yes? Something like this.
So now I obtain, as I said, longer sequence in Tor. So this is just I need for one. multiplied by R over 3.
Mm-hmm. Mm-hmm. Ну, тут tensor product of R modulo I and R modulo J, yes. Mm-hmm.
Yes. So this is just the direct formula. And, this is 0.
Because R is free,
Hence
it's projective, hence it's flat, yes.
This means
That our Tor is just kernel, yes, kernel of I tensor ID. Mm-hmm.
J is isomorphic to the kernel. Yes. Kernel of this map.
Of I tensor ID. Mm-hmm.
So we need to study this map.
Mm-hmm.
Understand how okay.
No, yes, it's more or less, it's
long.
It's an explicit map,
Yes.
so you can just
But
write down what is what is this kernel.
it was not really obvious for me, so I did it in this way.
Okay, let's see.
We claim that there exists an isomorphism between this module and the R. Like this.
Ah, yes, sorry, maybe, what? Yes, what I wanted to say, that in fact, no, it's general fact, if you have module over R, and you consider tensor product of M with R modulo I, it's M modulo Mi. It's in general true. You want to see that this map is isomorphism?
Yes.
Yes, no, it's general for any, yes. Modulo this observation, of course, it's obvious, yes. For any M tensor I, of course, it's isomorphic to M modulo Mi. Okay? It's true for any module, no, by the same reason, I think. And modulo this observation, this, in these terms, this map more or less explicit, and it's more or less obvious what is kernel, okay?
Yes. Okay.
No, the map, yes.
I just can
Mm-hmm.
construct the map and I just.
It's generalization of the, if you consider with R, you obtain the same module. If R modulo something, okay.
Yes, yes. So.
Maybe, no, yes, M is right module, yes, it's true. In this direction,
Yes. So
in this order.
I'll just.
Yes, this map.
This map
Mhm.
is given isomorphism. So first of all, if it does not. So
No, in fact, I think you can define the opposite. No, okay. Let's check the injectivity and extractivity.
First of all, I just check that it does not.
It's correct. Yes.
Yes, the correctness of this number.
Okay.
So if we take.
Maybe we write here M, and because I think it's not important. It's ideal. Okay.
Okay.
I think your argument are still valid.
Okay, but I'll write I to.
No, I is element of M.
Yes,
Okay.
yes. Okay, the correctness is obvious. I don't know.
No, yes.
So this is I. This is
Yes. Okay, it's correct homomorphism of.
Yes, and now.
In general of abelian groups, because in general this is not R modules. If R is not commutative, it's homomorphism of abelian groups. Okay. Mm-hmm.
And I need a map which goes in another direction, so psi.
Okay.
So this is obvious map. It takes an element. It takes the class.
Of I.
So it sends it to I times 1.
No, yes, of course.
And
also you can check that it's correct map. Yes. No, in the same manner, I think. No,
Yes,
it's modulo G. It's modulo G. It's more or less
Yes, correct.
obvious because you
Correctness
can.
is obvious.
Yes, because
Yes,
it goes,
I can-
yes, you can move R to yes.
Yes, of course. And I mean,
No, and then you can check that this is inverse isomorphism. Okay, yes, it's right. Yes, okay. So of course this is true. Okay. And the model of this observation, if you interpret this tensor product as this quotient, then this map I tensor ID it's very explicit, and you then can check what's kernel. Yes.
I will just write what it is. This is this is a map to this, and this is part tensor. I wrote like this. Okay. So it is okay. So this is psi. This is I over I. And when we compose, this.
No, and here you also can. Maybe you can say that this is R modulo J. Maybe in this terms it's more explicit. No.
Yes, this is just this class I to I.
No, yes. To I, no, also class.
Class,
yes.
But in
modulo J, yes.
So in this.
No, in these terms it's obvious, more or less obvious that what's the kernel, yes, because yes.
So it's isomorphic.
No, it's elements of I which goes to J. It's elements of intersections, no modular product, yes.
This is I plus
such that I in fact in J. And it's in I by definition. So yes, of course. Okay. Yes, you're right. Okay, thank you. Okay, good. Now what about examples of extensions? Yes. Okay, let's give you some rest. Let me say about not flatness of xy. Some cheating way of proof of this. Example of torsion-free but not flat module. It's ideal xy in polynomials in two variables over some field. It's torsion-free, but it's not flat. Why it's not flat? No, in general, we have something like. In general, of course, we need to find some injection which tends to not injective map after applying tensor product with I. No, of course, it's inclusion of I itself to polynomials, because after tensor product with I, let me note it by R. It's something like this. And in fact, for example, something like this, it's not 0 in the tensor product, but it goes to 0 here. But maybe it's not very obvious, but why this is tensor not 0. And now we can check not flatness of this module in some a little bit less direct way. Now let's just again use long exact sequence in homologies for short exact sequence of definition of I. And I want to apply tensor product with K over R. And write down the long exact sequence in homologies and Tor. So I have something like this. R modulo R, it's K. I. Then Tor, K, KK, yes, K. Then it's 0 because it's Tor with R, yes. And then it's Tor Ki, Tor, second Tor, Kk. And again, it's 0, and it's the pattern here. So we obtain in fact that, in fact this thing is not 0, and this is not injective. But it's not, no, it's something like not flatness of k. It's more or less obvious. But here we obtain that tor I, if it's greater than 0, between k, k, always is isomorphic to, no, in fact, all higher tors are 0 because over polynomials, any module has a resolution of length 2. No, it's not important here. For example, okay, we obtain that second tor of kk is isomorphic to first tor of kk is isomorphic to the second tor of ki. And so to obtain that this is not 0, it's just we need to check that this is not 0. And this is much more easier to calculate because k is much more easier module than I, okay? Okay? No, I claim that this is not 0, and this is not 0. No, to calculate this thing, I need resolution of k. It's resolution of k. No, okay, sorry. Projective resolution of k is we write it down the previous time. It's r plus r. R is polynomials, yes, and r. Here is just x and y goes to 0, yes. Here it's 1, 0 goes to x, 0, 1 goes to y, yes. And here unit goes to the basis of relations in kernel of in I. It's something like y minus x or x minus y, something like this, yes. And now I just in the previous time I wanted to consider tensor product with I. It's not obvious. Now I just want to consider tensor product with k. It's much more easier. It's much easier. If I apply tensor product with k, I obtain k r. No, I don't need this thing. Yes, sorry. My resolution is free, so I obtain k plus k and k. And I think that all these maps are 0 after tensor product with k, because all these elements are 0 in R modulo k, in R tensor k. No, because in R tensor k over R is isomorphic to k. No, for example, what if I consider map multiplication by x tensor ID? Well, of course, it's 0 because it's in this identification. I identify one tensor 1 with 1, and if I have and now 1, it goes to 1 tensor 1, then it goes to x tensor 1. It's the same thing in tensor product as 1 tensor x, but x in k is 0, so it's 0, and so it's 1 goes to 0. Okay. So in fact, all these differentials are zeros because it's x, y, and so in something like this, it's also 0. No, and it's easy to calculate the homologies of this thing. I obtained that the tor 0 is k. It means that k tensor k modulo polynomials is k. Okay, and the first tor is k plus k. It's k plus k. No, and second tor is k. It's k again. Okay. Okay.
What do you mean by? I mean, why do you need? For what reason you calculated k tensor k?
No, it's tor 0. No, it's just example. Maybe it's not obvious from definition, but from this observation we see that the 0 tor is k, and this is k tensor k, of course, by definition. Okay. So in fact we obtain something like this, and we obtain that the first tor is k plus k. It's not 0. So this tor is also not 0. So I is not flat. Okay. No, in fact, no. For example, if you calculate tor 3, you obtain its k, and this tor 3, this unit k in fact goes exactly to xy minus yx. In fact, it goes to the to this element. It's correction of not exactness of the tensor product with I. In effect, no, you can check this in general. You can check how this coincides with the previous observations of not exactness of tensor product with I. Okay, it's this observation. Some easy exercises, but no, maybe we will use them today or the next time. So let's not just state them. If I have short-tangent sequence of modules, if two of them, for example, are flat, can you say that the third is also flat? Is it true or not true?
I think yes. Maybe it depends where they stay.
Yes, of course.
If we write long exact sequence on Tor, maybe
yes. Tor I M A I M B Tor I M C Tor I minus 1 M A and Tor I plus 1 M C. So if A and C are flat, it's 0. Then B is flat. Okay, obvious. So if A is, if B and C are flat, then again this is 0 and this is also 0. So A is flat. Now, of course, if A and B are flat, C is not flat in general because we have short sequence Z modulo n. Okay, over Z. It's not flat. It has torsion. Okay, and you can check the same thing for projectives and injectives. For projectives, I think it's the same third from two others, and for injectives, I think it's another place of the third module. Okay, no, it's just it's easy observation, but maybe we'll use it today. For example, over abelian groups, we know that in fact, because second Tor always 0, we obtain that every submodule, subgroup of torsion-free group or flat group, it's flat. But in general, it's not true. It's true only if quotient is also flat. If these two flat, then it's flat. But if these two flat, it is flat over any ring. Okay. No, I just recall this because remind this because I want to use this today on the lecture. Okay. And the exercise of the crucial importance for our today our considerations of spectral sequence on lecture is the resolutions of complexes. Let's recall. Is it obvious? No, I just recall. If I have chain complex, I claim that there exist projective resolutions of each module of this chain complex of the following form. In verticals it's resolutions, yes, and in horizontal way it's just of the following form: P I J is B I plus 1. No, B. 1 second. Okay, let's B I plus 1 J plus H I J plus B I J, and Yes. And it's as modules. And horizontal differential, no, it's 2 pi p I j minus 1 b I, sorry, no, I minus 1 j, sorry, p I j plus h I minus 1 j plus b I minus 1 j. No, this differential sends this to 0 and sends this to this identically. Okay? It's horizontal differential in each level. And this is just as modules. And you have some vertical differentials. Additionally, no, this is projective models, and all these models are also projective. And additionally, if you restrict vertical differentials to this submodule, you obtain a projective resolution of homologies. It's projective resolutions of homologies, of I homology of C. Is it obvious that such thing exists? Because no, we will use this thing. It's even have something, some name, something like Cartan-Elin-Bierk resolution of chain complex, something like this. No, it's useful. It's a generalization of resolution of short-like sequence. Yes. If your sequence is short and exact, you have no homologies, and we obtain something like this. We obtain that this projective resolution of this, projective resolution of this, and this is the sum of these two projective resolutions. It's more or less the same thing. But this is generalization to the chain complexes of arbitrary length and not exact with homologies. Is it obvious? No. Okay, then let me say something about this. No, it's again. It follows from observation that chain complex is more or less equivalent to two sequences of short-taken sequences. I have one short-taken sequence. It's no. Let me denote no, Z. It's kernel of D. Yes, it's kernel of Ci to Ci minus 1. Yes, it's Zi. It cycles. Mm-hmm. And Bi is its image. Maybe 1 second. Bi. No, yes, it's image Ci plus 1 to Ci. So it's boundaries in Ci, and this is in Ci. Mm-hmm. Okay, it's submodules. So I have this exact sequence, and quotient by kernel, it's an image of the next. No, it's image in the next module. So it's Bi minus 1. No, model isomorphism, natural isomorphism. Okay. And you have, because it's chain complex, the boundaries are in cycles, and the quotient is homologies. Now let me denote this is homologies. Okay? So, and we can construct projective resolutions of short-like sequences. Now let's do this. Now let's start from second one. Choose any projective resolution of boundaries. It's any projective resolution of boundaries. And any projective resolution of homologies. Then, by our previous construction, we can construct from this the projective resolution of cycles of the form of the sum of modules. It's not sum of complexes. No, 1 second. It's as modules, it's sum of these things. Differential here is not sum of differentials, but no, yes, it's not sum of differentials, but it's some things. Okay, it's this composition and this lift, yes. You have these two maps, and so you have these maps. No, in general, it's not just this differential, it's something like lift in this composition. This is this differential, and this is not this differential, okay? But anyway, we obtain projective resolutions of cycles, and then we can apply it here and apply it here, bi, and so we have cycles with this projective resolution.
What do you mean we can apply it there?
No, to use our construction, we need, if you have short sequence of complexes, of modules, to construct projective resolution of the middle term, we need projective resolution of.
No, this I understand. So we just construct another projective resolution for the.
No, yes, we choose any resolution of B, any resolution of H, we obtain some resolution of Z. And now we have this resolution of Z and resolution of B, and we obtain resolution of C. It's what I say now. Okay. And here we have the same resolution of B. And again, from these two resolutions, we can construct resolution.
Okay.
And this is of this form, in fact. No, and you can check that this works. This is resolutions, and more or less by definition, how to glue these short arc sequences to chain complex again. No, you need no, you need differential is Ci goes to Bi minus 1, then it includes to Zi minus 1, and then it includes to Ci minus 1. This is differential, yes? No, by definition, more or less. No, if you do, and so from these two sequences, you obtain again your chain complex. And if you apply this observation to these resolutions, you obtain chain complex of resolutions of this form, of differential of this form, exactly. And from these properties. And that this is a resolution, it's more or less the same thing. You can check this because here all differentials are explicit in most explicit. So yes. No, yes. No, here, in this map, all this goes to 0. This is all goes to 0 because in the kernel. And this map goes directly to the next step as a building block of the next step, identically by definition, more or less. So if you need differential, you have here it includes to Pi minus 1 dot. No, and this is differential. This is in the kernel, and this is identically, as I claimed. And so this is definition of horizontal differential. So I defined this sequence of resolutions. It has this form. No, and okay. 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 Now let's you say us about extensions. ZM. No, we will use these resolutions today, or maybe no, more or less today, or maybe next time. So it's important. Oh no, this of course today. And it's important to understand this thing. It's more or less obvious that it exists if we can do this construction for short arc sequences of modules. Then it's more or less obviously generalized to chain complex. Okay. What about extensions?
Because this is very simple.
Yeah, so we want to consider extension. So as we calculated,
you now want to recall us the construction of bijection?
an isomorphism of this form. So if we consider extensions of right z.
No, yes, no. It's of course it's more or less explicit bijection. We have resolution.
So extensions of this form.
No, because this resolution very simple.
0 zm x zm 0. Yes, yes. So, and we have this. So, the previous time we constructed this isomorphism explicitly.
Extension corresponds to x class is very explicit.
Yes. And we need to. So we have this explicit isomorphism, and we just need to take some other isomorphisms to get there. So, and this is the place where what I wrote
on the right,
contradicts to the internet data. So you will correct me. So M and
yes, this extension corresponds to x class is very explicit. Yes.
GCD of M and we need to go that direction. So the first isomorphism goes like this. So okay, let me take K prime and send it to M divided by D times K prime, where D is once again is GCD. And so this is a generator, like this. Okay. So.
What is fact? When you prove, and we need to go this direction. So it's fact that Z M modulo n is isomorphic to Z modulo this common divisor. Then, in fact, I think you prove it by consider by solving solving the equation that m times something is unit modulo n. It's something like inverse number. Maybe it's not k, maybe something like inverse or something like this. I'm not sure that this is exactly the same. But in fact, when you proved it's fact that Z m modulo n is isomorphic to Z modulo this common divisor, then in fact
why does it matter?
I think you proved it by
but
consider by solving
this. You want the
by solving the equation that m times something is unit modulo n.
Okay, we
it's
can
something like
construct the inverse
number. Maybe it's not k, maybe something like inverse or something like this. I'm not sure that this is exactly the same isomorph which you said before. No, maybe, okay, no, of course this is isomorphism. No, maybe you can check that this isomorphism directly.
Why does it?
No, unit isomorphism, yes?
Yes.
No, this is isomorphism, then let's check that it's isomorphism, okay?
This?
Yes.
Okay, we can construct the inverse.
No, I think in the inverse you need the same inverse modulo m or something like this again. Yes. No, okay, let's.
So I don't have a concrete check this, so let's just see what we have. So
Okay, maybe it's not important. Maybe okay, let's believe that it's isomorphism. Maybe.
phi of k, and this is just k itself, which is just 0 over d. Yes, I guess you're right. We really need an explicit construction. I don't remember how I checked this.
No, okay, let's believe it. Okay. This is the motions, and then the second one.
Okay, let's denote it by k, and this will be some number. And here, by construction, it goes to the map. So this is a representative. So this is a map from f1 to Vn. We denoted it by xi, and this sends r to, will send r to k. So I think I need to prove this, yes? Yes, because, and here I need to take my phone because I did this calculation today in the morning and I just screenshotted my blackboard. Yes, so to see this, we need to consider so we need to return to the beginning when I calculated the x by definition. Yes. So this is home AB, ZDM. Oh, another direction. This is multiplication by n. Home AB. 0. And we need this explicit maps. So the explicit maps, as I said, they are maps phi, which send which send k to phi of phi k, which is by definition.
It sends 1 to k. Yes.
Yes, it sends 1 to k. Yes, and here when we compute this homology, so cohomology, this cohomology of the of this sequence is what we need. This is m. Yes, and we have an explicit map phi star induced on cohomology, which is so which goes to x. This is what we need. And this is by definition, yes, just by this. This is home Zm factored by image of this map, something. So and how does it work? So it works like this. It sends k to equivalence class phi of k. Yes? And phi of k is just phi k, as I said. Phi k. Here, yes. And what do we have here? So this is basically it. We take k and take.
So xi is phi k. It sends 1 to k. What is it?
This is r, and r is sent to k.
No, then r goes to rk. Yes.
Yes, okay, let it be. So this is just by definition because here there I had 1, and
yes,
so
yes.
this is it.
Phi k. Yes. It's phi k.
Yes.
Okay, and then apply explicit psi. Yes.
Yes, and then I apply. So
In fact, so far I think this is all true.
no, because I thought so. The main struggle was this Isomorphism. So here was my struggle. Here, because I thought that this is right. It seems very correct. I mean, we divide by the greatest common divisor. We act.
What the struggle? What the contradiction with internet?
Okay, we will get there.
Yes.
So here we just need to use by definition. By definition, we send this to xk class xk, and our class xk.
No, yes, clear the right side and write down the extension xk.
By the way, at first, when I started to, when I just started to think about this exercise, I thought this will be very messy calculation, because when we constructed this isomorphisms, that was a huge deal. But when we think in these terms, I think this is very nice. I mean, it's easy to use construction.
No, I think because the messy part is the opposite direction, maybe isomorphism, and this psi is very, very explicit.
Yes.
If you already believe that this is extension and so on, and this is very explicit formula.
Yes. So by definition, this is ng.
Yes, something like this.
So
but I think this is true, in fact.
I mean, I'm just doing everything by definition. This is the place where I need to write this.
Yes, I think this is true that all extensions have this form. It's not true? I think this is true.
This is true. But you will see in a second. So this is obviously This is obviously m0, kn. Yes. So this is of rank 2. This is and just by classification theory. Okay. So this is right here an image of A. Where is this matrix? M0 kn. And by classification theorem, this is rank 2. Hence, this must be isomorphic to zd1 plus zd2, where such d1 divides d2. And so, as far as I understand, we can take d1.
No, in fact, d1 you can take
Yes,
GCD
of everybody.
All these elements and
okay, this is D.
It's common, yes, here.
Yes, of course.
And D1 multiplied by D2 is just determinant. It's mn. Yes. So yes.
And m minus 0. Okay, and you are right. And from here I obtained.
What is it? What's the?
It's module. It's determinant.
Yes.
Determinant. I calculate determinants, so this is
it's an M.
mn.
It's triangular, yes.
And this is d2 is just.
Yes. It's right.
Divided by d.
No. Yes. Maybe. Not very obvious thing. It's how. It's just group. How extensions looks. How embedding looks. And how projection looks. Maybe it's not.
What do you mean? No, we constructed it by explicit
of course, but okay, no, in these terms. Maybe,
I think you need
because this diagonalization algorithm. Maybe you need to understand in these diagonal terms how this works. Yes. In this term, but in this term, it's maybe a little bit less obvious.
Think you're right.
How this embedding looks. Because it's maybe not obvious, and this is point here. Yes.
Yeah, I forgot to do this.
Yes, of course. As groups, it's all groups, but embedded may be different. In the same group, for example, if you consider in the same group you have different embeddings and different perspectives. This is the point, and this is why I give you a simple exercise about p squared and pi and p and something like this, because in general maybe it's you need this diagonalization algorithm in general.
We need to take some bases like this.
Yes, and you need some projection on this new base.
Yes, and compose with everything.
Yes, and then compose, and then you obtain answer. And for example, for something like this. This is true, but yes, and so we obtain that extensions has something like this form. Yes, the m to z d plus z mn d dm, where
Yes.
d is GCD of mn and some k, where k is modulo GCD and m. But these embeddings, no, they maybe they in fact they no yes, they depends on k, not only d, because maybe for some different k's d is the same. So this embeds depends on k and y depends on k.
So the difference, the internet says that we need to take, we can, so okay, let's just focus on this answer. Internet
Okay.
says that we need to take k from 0 to d, yes, to d minus 1, yes, to d minus 1. And so this is what internet says. But what I calculated, I calculated this, maybe this is the same, I haven't thought about it, but we need to remember that we have k of the very explicit form. So from this calculation, it's so we have that k is of that form. M divided by d times sine k prime. Maybe this is the same. I haven't thought about it. So from the construction, it must be the same, but yes.
No, maybe we consider some simplest examples where m and n are prime or something like this.
I thought only about z2 and z2.
Z2, no, for example.
Yes.
If you consider Z2 and Z2, it's the same as Z prime and Z prime. It's not harder.
Z prime and z prime. Yes, but okay, this is only the only thing that I thought about, and everything is correct in this term.
No, yes, and so as group, we obtain if m and d are prime, m and n are prime, a p, then GCD is also p, k is also
Yes.
p, no, k prime is p squared modulo p is also, no, sorry, it's k here, 1 second.
P. GCD is p.
It's p k, yes, it's
Yes.
embedding. You consider some invertible element modulo p, and then consider this embedding, zp modulo to zp squared, something like this. Oh, sorry, zp zp to zp, to something like this. Zp modulo, no, yes, to zp it's multiplication by k. You consider this thing, yes?
Yes.
So, yes, it's k prime, and then blah, blah, blah. No, and so here you obtain that this is unit, this is 1,
Yes, and this is
because where definition? No, because it's pp and some coprime is p, yes, so it's 1, so it's 0, yes, and so it's this is p. Sorry, not p squared, yes. This is always p squared because d is 1. So this is always p squared. So they look similar, but embedding, but you have, except of one case when k is 0. When k is 0, it's splitting. Since if k is 0, this is 0, and in fact then if k is 0, then d is p. Then d is p. Because no greatest common divisor of 0 and something, this is something. Because 0 divided by anything. So if k is 0, then this is p, and this is zp plus zp. So you have trivial splitting extension corresponds to 0. Yes. It's only 1. It's k0. And you have p minus 1 non-isomorphic extension of these forms. No, in fact, where here unit goes to something like k, and k is invertible. No, kp, where k is invertible. No, this is different extensions. They are not isomorphic as extensions. Something like this. No, here, yes, here this embedding, here this diagonalization more or less obvious. No, because here, yes, if you have P, and K. In fact, no, in fact, it's more or less obvious that this is, no, maybe, yes, maybe here, maybe this is not K again. Maybe it's some alpha, but its alpha depends on K, and if K runs through all invertible, alpha also runs off all invertible, something like this. Maybe it's inverse to K modulo P, I don't remember. It's something like this, okay? Maybe it's K, no, alpha depends on K, and when K is from ZP invertible, then alpha is also from ZP invertible. So they indexed by invertible elements, something like this. Maybe it's not K itself, maybe, no, maybe it's, for example, maybe it's invertible modulo P for K, and something like this, okay? No, you need this diagonalization algorithm and see what is this. It's not very hard. Okay, and no, I did this, in fact, but maybe we don't need this. Guess what? I did this diagonalization algorithm. In fact, no, it's some kind of Euclid algorithm, yes, because you need some rows and column summands to obtain greatest common divisor. It's some kind of Euclid algorithm, in fact. No, and yes, and for example, if you consider, no, and the same thing you obtain if you consider Z and Z modulo P, you obtain, in fact, no, one splitting extension. And P minus 1 non-splitting extension of this form, where here is P, but here its unit goes to some invertible element of Z modulo P. They're all also not isomorphic as extensions. But if you consider, for example, Z modulo P squared and Z modulo P, for example, something like this, then, or maybe, no, maybe, okay, for example, yes, Z modulo P squared and Z modulo P. Then, no, in fact, you have, at least you have three groups, three different groups. You have, no, yes, I want to consider something like, just 1 second, modulo, I remember, modulo P or modulo P squared, what's the order here? I want to consider, 1 second, what I considered, the simplest example. What here, Z? Yes, I consider Z to ZP squared, what, something like this. I consider X, no, it's the simplest example, yes. ZP squared, Z, ZP squared, yes. And now you have three different groups. Now you have the splitting thing. It's one as extension also. You have you have these groups. Where here's P squared, and this is multiplication by some element inverse modulo P squared. But these elements, there are P minus 1 of these elements. No, coprime with P squared, yes. And you have elements which is divisible by P, and they then give you extension of the form of this form. And you have P minus 1 extension of this form. Где я сейчас только что это говорил? Something like this. Something like no, here it's one goes to I think something like pk, something like this. No, and this in fact it goes 1. Oh, sorry, maybe. Okay, I don't remember. But you have alpha where alpha is zp invert. I don't remember the explicit formula, but you have p minus 1 extension of this form, something like this. So you have 3 different groups and p squared different extensions. Okay, something like this. No, you can как сказать, восстановить детали.
Restore the details.
Как?
Restore the details, I don't know.
No, okay, something like this, yes. Yes. What? Where it needs to go? Something like unit. No, okay, yes. It's kind of exercise. No, yes. For general M and N, and it's more cases, maybe, and something like this. Okay. So extensions. So the points here, it's what the explicit embedding and projection modulo this diagonalization algorithm. As groups, yes, it's true. What the contradiction with internet? It's some restrictions on D, yes, on K, yes.
Not really restrictions. So there is no restriction. There are different formulas. So they say we need to take K, like 0, 1, 2, 3, and up to D minus 1.
No, okay, yes, no, it's.
Yes, I wrote that this is.
No, I think it's okay.
Divided by
Yes. No, for example, what if you consider z6 modulo z, no, for example, z3, z2, I don't know, x, yes. What the x? Z, yes, z, yes. What I want to say? Z2. Yes, z2. Yes, and what the 2 different extensions? No, you have.
trivial.
Yes, you have trivial extension. What the non-trivial extension? I don't remember what I want to say, but I think it's something like this.
Maybe the group is the same, no? But as an extension, it is not this. Yes, it is. As a group, it must be the same because this is Z2, you see, and we have class Z. This cancels. As a group, it's the same, but as an extension,
Yes. Then it's not. Yes. Then I think I want to consider Z here. Sorry, it's Z6. And we have a trivial extension. We have 2 extensions of the form where it's Z. No, sorry. How invertible modulo 6? It's 2. It's 2 invertible modulo 6. Yes. Yes. It's 1 and minus 1.
Okay. Yes.
Yes. So we have this thing. We have invertible. It's of the form of this thing that goes plus minus 1, and this is. And also you have 3 other things corresponds to 2, 3, 4. Yes. And what of the form of the group here? D is 6. No. Yes. D is 6, and it is the 6, the Z modulo 6, and Z modulo. What? N is.
I cannot calculate it.
N is 0, yes, and M is 6. No, it's then it's something like what it is. No, I think that it's something like z modular. No, I something like maybe something like this. And for z2 also. But for example, here you can sense 1 to 1. I don't know. 1, or maybe 2 here. I'm not sure. No, yes, and maybe not 2, maybe what 2 or 4. It's plus minus 2 here. And then quotient is z6. And you also has these things. E plus z2 goes to z6, where it sends to 1 to 3, 1. But I think something like this. So, no, it's, and this is z here. And so, in fact, you have much more non-equivalent extensions in general thing.